That's the proton pencil beam scanning mode, because all the modern proton therapy facilities are doing this now. See, the passive scattering mode that I described, that uses hardware. You have to have a compensator, you have to have a range modulating wheel. What range modulating wheel is? Just rapidly rotating and putting variable amount of material in the path of the beam. So the pristine Bragg peaks are shifted to proximal direction, and they combine, you get a spread out Bragg peak. The apertures are used for conforming to the shape of the target. A range compensator is used to compensate for the differential depth, distal depth of the target. So all those things are needed to be manufactured for every patient. So passive scattering beam or double scattering beam is very hardware extensive, that you need to have those things done. So now I briefly described what the scanning beam is. You have the narrow beam, now time to get up. Okay. It's a narrow beam that is coming out of the accelerator, is dynamically changed to different locations with these two scanning magnets. And then if you want to irradiate this one, then you adjust the energy of the beam by asking in a synchrotron different energy level, or putting a range shifter here, or using the energy degrader to choose your range of the beam. So the some of the spots, pencil beams will go there, some will go here. So that's why the dose will be conforming in the longitudinal direction to the depth, deepest depth and the most proximal part. So that's what happened. So even how lateral profile is, this is in the longitudinal direction. How the lateral profile is evolving, because you have a spot here, spot here, spot here, spot here. You combine them, then it will give you a uniform field to irradiate the target uniformly. So the scanning magnet is doing the trick. Okay, it is providing the spots at different locations, and if you combine the spot profiles, then you get a uniform beam dose there. Okay, that is what the scanning beam is. Let's see what my next slide is. Next slide is nothing, same things. Okay. Okay. My friend, can you look at it why it is not working? Is working now? What? This is a laser, but moving.
The sensor, the sensor not charged. That's why that.
Okay, no problem. Yeah. I can start my. It's working. Okay, let me go back and close it and start again.
It's probably this issue.
It's not charged.
It's working.
Okay now?
Yeah.
Wonderful. You have a miracle hand which does miracles. Okay.
Thanks.
You have good hands. Why? Not here. Why is right so? No, not from current side. Sorry. Okay, we are getting there. Okay, everything is good. No worries. Okay, so. Yeah. So this is what happens. Let's see what is your next slide. So this you will see dynamically what happens. This is the pencil beam here. You have two scanning magnets, and you have a target layer that you wanted to irradiate. then you send a spot there, go to different location, then go to different location, then you have a different layer, proximal layer, and in order to bring the energy there, you either you choose the different energy from the synchrotron or put an energy shifter there or energy degrader. So if you have energy selection, you select the energy so that the next spot will go to that proximal layer, and you continue, move from deepest layer to the proximal layer and scan the and put the proton beam wherever it is needed. Another way also you can see here, this is called discrete spot scanning. In discrete spot scanning, you put the spots one by one, one by one. The one spot is delivered, there is no beam. Another spot delivered, no beam. But you can also have a continuous scanning. We are trying to reduce the time between one spot moving from one spot to another spot. So you can just continuously also move the spots. That is possible nowadays. It was the technology was not available, but now it is becoming available. That is called dose-driven continuous scanning. That's a new technology that is going to be is gradually being introduced. But look at it how it is done. First, the target is separate. This is your target. The target is separated into different layers, deepest layer and the proximal layer. Okay, and then a layer is divided into some possible spot locations that where the spot can go. That's all the available spot location. And how do you decide what are the spot location? Because you decide in your planning what is the spot spacing, that how much of spot spacing you wanted to use in order to deposit those spots. Okay, that is the planning parameter. So once you decide that, then spots are irradiated one by one. Let's see how it is done. You go to it goes to the deepest layer. You see, this energy is irradiating this deepest layer now. Okay, and then you go to same layer but a different location, and then you move to another layer, proximal layer. So you can see the energy is reduced, the black peak is somewhere else, and you are doing something another layer. And that's the same layer. After finish, you do layer by layer, and then all of them are combined. Then you get the uniform dose what you want. Okay, this is giving a uniform dose to the target is now normal standard. Okay, normal practice, because physicians have but something, the biology from radiation oncology, radiation biology, it is probably in the early stages when we used to do 2D planning or 3D planning, that was a good concept. But now with intensity modulated planning, we can give what in a target whatever dose you want. Only thing we don't know that what dose to give where. Okay, once that is determined by other means. Okay, suppose you have a PET scan. Okay, you did a PET scan of a patient. PET scan provides you functional imaging, that how the tumor is functioning, how much sugar intake. Okay, PET scan is probably giving you the sugar intake of different regions of the tumor. And there is a hypothesis sugar intake depends upon how aggressively the tumor is active. More sugar intake, the tumor is more active. So if you know there is a sub-compartment of the target which is very active, aggressively active, we can probably, we have a very good biology geneticist there. Okay, so he will tell us maybe there is some correlation with the nature of the target with the intake. I am giving one example. That may not be true. The sugar hungry target is the cancer cells are hungry for energy, they take it. We think that a hungrier target is the most dominant part of the cancer that we need to eradicate. That's a hypothesis that has to be proven, and that is proven in some sense, in the sense that within the target, when you go to discuss treatment planning, there is something you define gross target volume. Then there is a clinical target volume. So then within the gross target volume, you can have sub volumes. You know, in treating head and neck cancer, normally the physicians defined 4 or 5 targets. Some peripheral target to a low dose, interior target to a higher dose, more interior dose to more higher dose to another interior dose, and very small volume, very large dose. So that's why I am telling you that this concept of giving a uniform dose may not be possible, may not be necessary. But intensity modulated proton therapy, volumetric modulated arc therapy, or simple intensity modulated radiation therapy has the capability to optimize your dose distribution in a non-homogeneous way. That is called simultaneously integrated boost. You are treating a large volume to a large dose, a small dose. You are gradually reducing doses to, you are giving higher doses to selected sub volumes of the target simultaneously. That is something called a sequential boosting. In the sequential boosting, what you do is you give a dose to a large volume for some time and then cone down and then give some dose to a smaller volume and all kinds of things, because it depends on the target how much dose you need to sterilize. The whole aim is just to disable the target, that cells, cancer cells, to stop dividing. Okay, disable them to divide or stop them dividing, and that's what the goal is. So this digression I made just to tell you that this is the concept that giving a uniform dose has been there for a long time, and we are gradually changing that paradigm. The paradigm is to identify where the most dose is needed and then give it to them. Okay. Okay. So this is the nozzle of a spot scanning nozzle. Beam comes here, there is a profile monitor. This profile monitor is there in the passive beam also. What this profile monitor does is that the beam that is coming out is checking if this beam has the correct parameters or not. Okay. If the beam coming out is polluted, is corrupted, or not up to the reference profile that you are looking for, then beam will stop here. It will not go there, and you need to look at your oscillator parameters and extraction parameters, make sure that beam profile is properly restored. Okay. Then we have a scanning magnet that scan the beam to different directions in XY direction. The scanning is done in XY direction and then goes through helium chamber. Then there is a spot position monitor. Because you are moving the spot from one location to another location, you have to make sure that spots are going where they were supposed to. If they are not going, there was an accident happened in Germany. Somehow the scanning magnet was not working. All the spots go into one location. Imagine that this dose is very high, the patient died. So this is very critical that your spot position monitor, you have a way to monitor that spots are really moving. That can happen in a linear accelerator also. In a linear accelerator, or when you are delivering intensity modulated X-ray therapy or volumetry VMAT, the multi-leaf collimators are moving as the beam is rotating, moving. If they are not moving, you are giving the dose very large volume dose to unintended dose to a large volume, and then patient will have adverse effect. So that is the most important dangerous thing in this business. Okay, so you have to be very careful about this. Make sure that spot position monitor is working very well. And then of course you have dose monitors that counts the protons and making sure the number of protons you planned is giving. That's called a dose monitor, or we call it a monitor unit. That's a monitor unit counter in also Linux X-ray machines. Same also here. There's a lot of concepts are borrowed from the X-ray machines. We have to have a way of counting the protons and terminating when they reach the number of more protons we wanted to deliver. So sometimes you can use an energy filter or energy observer to bring the dose to the proximal level, because you have a 70 MeV beam and the range is about 4 point something. It can penetrate up to 4 point something. But sometimes the target are very superficial. How do you want to treat? Because your machine is not able to put the Bragg peaks in the proximal region. So you want to shift those spots to the proximal region. Then either you put an energy filter or you put an energy observer. They do the energy filter is something called actually I have to take. I'm sorry, I gave a wrong explanation. Energy filter is sometimes called a Rees filter. In a Rees filter, what you do is you broaden the Bragg peak artificially. Broaden the peak artificially by putting some peaks and valley like a energy filter. So what happens is, in that way your energy, the Bragg peaks become a little bit broadened by 3 to 4 millimeter more. So that's why you may not need that many energy layers, because if you have a very narrow peak, then you might have a very different large number of energy layers has to be selected. But if you have already expanded the Bragg peak by 3 to 4 millimeters, then what happens? That will cover large amount of target also. So you don't need to have so many energy layers changing. Energy layer changing in a synchrotron or even cyclotron takes time. So in order to have a quick dose delivery, you don't need that sharp Bragg peak. You can live with, the dose delivery will be optimized, or the number of energy layers will be significantly reduced by using energy filter. Of course, these are low energy materials, so they will not create large number of neutrons, but they will help you to reduce the number of energy layers. Range shifter is energy absorber, or it's also called a range shifter. That range shifter will shift the position of the Bragg peak proximally. Energy filter will spread the Bragg peak to make it wider. Let's go back and make this concept little clear. Okay. So you see here, this is the Bragg peak here. This is the Bragg peak here. Suppose this is 2 millimeter. Suppose you wanted to increase it by Ridge filter to 4 millimeter. So in order to, this 4 millimeter Bragg peak will cover about 4 millimeter of thickness of this material. If you have 2 millimeter thing, then you have one layer here, another layer here. If you have a 4 millimeter Bragg peak, it will cover up to 4 millimeter. So that you don't need another layer of another spot of a different lower energy. So that's the concept. We have done some experiment and not experiment, some calculation, because if you put something in the path of the beam, the lateral profile will also change. The lateral profile will be broaden, because you are not only sparing the organs at risk by longitudinal penumbra, most of them are by lateral penumbra. If your spot size increases, the lateral penumbra increases, then you may irradiate a lot of normal tissue. Your lateral follow-up may not be that sharp. But we saw that it is not that, the change is only sub-millimeter level, okay? And also we can optimize them. We can optimize them by putting the proper spot spacing and all kinds of things. You can still get a sharp penumbra, lateral penumbra, even if you use a Ridge filter, okay? So these are some of the, of course, if you put an energy absorber, if you put a Ridge filter, it is no longer hardware free. You know, just like we get out of a passive beam because we don't want to use any hardware. But now we are putting some hardware, but they are essential and they are low G objects. So they are not really creating a lot of neutrons. Only when you have a high G material in the path of the beam, like the range modulating wheel, it is mostly made of aluminum, and then the apertures are made out of brass. So those things, they produce a lot of neutrons. So the neutron contamination of the scanning beam compared to passive beam is about 1/10 to 1/30th of what you get in a passive beam. So the secondary cancer risk from neutron contamination is pretty low in the scanning beam. When the proton and heavy ion therapy were contemplated, or people are thinking about it, one of the concern is that we will cure the cancer, but we will induce a secondary cancer by neutrons. There is a very well-known radiobiologist, his name is Eric Hall. He has written a radiobiology book. This book is read by all the physicians, okay, and physicists. Eric Hall, radiobiology book. He is a very well-known person. So he grew up in X-ray, doing X-ray and brachytherapy, all kinds of things. And when suddenly this proton beam started become popular, he raised this alarm that you are going to create all these secondary cancers because of a neutron dose contamination, neutron dose. But so many patients are treated, and it has been shown that from the statistics, from the outcome data, the secondary cancer risk from the proton therapy beam is not more than what you get with X-rays. And specifically with scanning beam, it has reduced significantly, okay? So if somebody asks what is one of the advantages of a scanning beam, the advantage of scanning beam is you don't have any hardware to be used, so that you don't have to have a machine shop to make them, okay? The Ridge filter and energy absorbers, they are universal. They are used for every patient. Once you get it, you have it there. And but you don't have to have a compensator. You don't have to have a customized apertures. Not always. Customized apertures are used in some cases because you wanted the sharpest penumbra that is possible, and that may not be possible by intensity modulated proton beam. Because suppose you are treating a lesion in the somewhere in the nose area, okay? The eye is nearby, and lenses, and there are many structures you wanted to protect. So you have to have a sharpest penumbra as possible. So that's why sometimes we use apertures on selected cases to sharpen the penumbra. And in a Mavian machine, Mavian proton therapy machine, the spots are very large. The spots are very large. So if you have a large spot, then naturally you cannot really confirm the dose to the eye area and all kinds of things. So they have something called a dynamic penumbra reducing collimator. So what happened is because that collimator moves to different spot location and sharpens the penumbra. It doesn't sharpen the penumbra in the interior of the target. You don't need it. Only in the periphery of the target where the critical organs are situated, they do that penumbra trimming, penumbra trimmer. That kind of penumbra trimmer concept has been there since cobalt 60, because cobalt 60 used to be, because of spot size, used to have a very large penumbra. So in order to reduce the penumbra, you put a penumbra trimmer, some kind of a collimator, okay? So Mavian beam has a dynamic collimation. They claim that by that way, they can reduce their, they can make a very high dose gradient for lateral OAR sparing. Okay, so you saw the scanning beam nozzle now. This is a Hitachi system. Other beams have similar things, okay? So synchrotron, our synchrotron gives us an option of 94 energy selection. You can request for 94 energies. Imagine if you have 94 energies, the job for a physicist, the job for the physicist is to do QA for all those beams, okay? So that's why we decided to go with a Ridge filter. So that way the number of energy layers will be less. And also, that is one of the reasons that we, instead of using all the 94, we are probably using something 70 of them. And still 70 is too big, but we have to do those QA, make sure that all the beams, the beam characters are not changing with time, okay? Gives good thing, gives you a sharper longitudinal penumbra, intensity modulated proton therapy, but then it increases workload for the personnel, specifically for the physicist. So this is what happens. The beam is, I have already shown you this slide before, as I was trying to see that what is the lateral penumbra here. You can combine the spots, get a uniform dose. You can adjust their weights, then you can get some non-uniform dose also. And these are the some spot sizes and that you measure in air, that how much are they. Low energy have a high, full width half maximum is pretty high. For 220 MeV is probably pretty small, okay? But remember one thing, this is measured in the air. As the beam passes through the body, tissue and all kinds of things, the proton beam goes through multiple Coulomb scattering. So the spot size changes, the spot size increases. So the kind of a trimming you wanted to do, the penumbra trimming, that works only for superficial lesions. After that, for deep-seated tumors, when the beam propagates through, that the multiple Coulomb scattering just makes the penumbra blurring. So you cannot really trim them that much, okay? So these are some comparison between passive beam and active beam. Passive beam is simple and mature technology because this has been done since the proton machine is used for treating patients. It's very inflexible. You have whatever you have. There is not much flexibility. Field specific hardware, loss of a proximal dose conformity, large gantry required, less sensitive to organ motion. Because in a passive beam, the beam is not moving. The beam is constant. Beam is staying wherever it is. But in active beam, your spot is moving. If you are treating a moving target, and the target is moving and the source is moving, and if you are not they are not properly synchronized, you may be treating the target at a certain other location than you planned for. So interplay effect, that's called the interplay effect. Interplay effect plays a significant role with the scanning beam. So you have to be very careful how to when you treat moving target with scanning beam. High proton loss and neutron production, that I have already talked about it. No field specific hardware, mostly no field specific hardware. Superior dose conformity is possible because we cannot do a proximal dose conformity with passive beam, but we can do that, achieve that with a scanning beam by choosing the energy of the spot. Normally there are a lot of things not in the gantry, so there's a small, not in the nozzle, so it's a smaller gantry, prone to loss of dose conformity due to organ motion. You have to have some kind of a gating or synchronization technique to make sure that spots are not moving spots and the moving target are not going out of a sync. Okay, you have to send the spot wherever the target is. So you have to monitor. One way of monitoring is put some fiducials in the target and monitor them by fluoroscope. If in the fluoroscope, if the targets are wherever you are near the target, in the target area, irradiate the beam. They move away, don't irradiate the beam. That is a technique being used, that's called a real-time guided proton therapy. That's fluoroscope guided proton therapy. But you need to put some fiducials in the target to do the fluoroscopic imaging and see them and then treat them. Okay? Make sense so far? You are all sold to have a passive beam, scanning beam. The other mode of treatment, I have to tell you that this is called uniform scanning. Mostly when they are not much used, but old centers they still have. In passive scattering beam, you have a fast scatterer and a second scatterer. But in this case, you have only one scatterer that spreads the beam little bit so that you don't get a very narrow beam, but you have a very decent size, 2 cm, 3 cm beam, and that beam scanned by scanning magnets. Okay, so very fast scanning beam, raster scanning beam. So that way you don't need a second scatterer. So what it makes, these are the scanning magnets. One is one direction, the other is in the perpendicular direction. So what it helps to have a higher dose rate because the beam is not going through any hardware to be scattered. So that's why there is not much proton beam loss. So that helps to keep a dose rate high and also reduce the neutron production. These are but still then you need to have a range modulating wheel if you don't have a synchrotron or if you are not using the energy layer switching. And then you have to have a compensator also, and you also have to have a beam aperture also to conform to the lateral extent of the beam. But these are the older technology used by IBA. Instead of having this second scatterer like Hitachi machine, they used to do this, and this was used to be pretty popular. But now everybody is into discrete spot scanning. Probably the new machines that IBM is installing, they don't have this anymore. This is just from a historic perspective as an information point, only for your information. So these are the, once you have the beam coming through the nozzle, then you have to bring the patient for a treatment. Then you have to have a couch or a chair, as I mentioned, the new development. And then you have to have some imaging system to localize the target before the treatment. In this case, what you are seeing is just to take two orthogonal images in our system, in the old system. You have a X-ray source here and another flat panel here, image receptor. So you can take a AP image, okay? And in this way, you can take a lateral image, okay? So in order to localize a target, find the X, Y, Z of your target, you need X, Y coordinates and Y, Z coordinates. So Y is common. The head to foot, that direction is common in both cases. One case gives you information from anterior to posterior direction. The other is giving from the lateral direction, the depth direction. So that's why you can get a radiograph, and that radiograph is compared to a digitally reconstructed radiograph from treatment planning system, and then you align them. As I mentioned in the newer systems, this is a very old system installed in 2006 when we started our proton system. But in newer proton therapy systems, you have X-ray system that can do cone beam CT in the treatment position. That's what we have in our new center. So you take a 3D imaging of the patient, and register with the treatment planning city and decide that how much shift you have to apply in your treatment position so that the target is properly aligned. Either the physician, sometimes the target is not visible in the cone beam CT, so in that case the bony landmarks are aligned. So the physician tells that how to align this patient. Either you are using bony landmark or a soft tissue, the target alignment. Some targets are very well visible, then you always align with the target. Okay, don't worry about the bone because you are not treating them. But sometimes they are not visible. You have no choice but to align them to the bony landmarks. So this is a IBA machine. Looks very what do you call it? Slick, and so that's what happens. So our machine, new machine, looks also something like that. But I don't have a picture. I have a picture. I'll show you. Okay. So let's summarize. Relatively low entrance, high peak to plateau ratio for unmodulated beams. I'm not telling that SOBP, spread out back peak, this is not true. That we have a longitudinal penumbra, which is about few millimeters. Lateral penumbra can be 6 millimeters. That is the 80 to 20 6 millimeter for 100 to 150. It can be 1 cm for other high energy beams. Can be azimuth for high energy somewhat larger than desired. Beam penetration can be controlled by adjusting energy or energy by range shifters. And this is a facility layout, how the proton beam is the penumbra that you see in the high energy beams is not the dosimetric penumbra. It is called geometrical penumbra because the target is too far for the high energy beams, so that's why your geometrical penumbra becomes larger. For low energy beams, you are treating targets at a closer depth. So that's why the geometrical penumbra is smaller. Okay. So these are the beam layout, facility layout in a multi-room facility. You have the linac or synchrotron or a cyclotron. Then the beam. This is the beam extraction path. Then every room has a chair, a couch, and gantry, and then beam can be delivered to different rooms. So in this case, what happened is you have a beam queue control system. Sometimes patients come here, they are set up imaging while other rooms are treating. You finish your imaging setup and then you ask for the beam. Depending upon who else is doing what, you will put in a queue. As soon as your line comes, you get the beam. So there is some waiting with this multi-room facilities. Okay. This is the Varian system, and same concept. They have a linac and then different rooms. This is a fixed room line, and these are rotating gantries. What next? This is a Mavian room.
One set of linac and cyclotron, how many gantry rooms can be?
Well, 3 to 4. If the one either cyclotron or synchrotron, it can fit to 3 to 4 rooms. Okay.
So at one time 4 patients can be
simultaneously be in the room for treatment. They will not be treated simultaneously. They will be treated one by one, but they can be in the room simultaneously. 4 patients, depends upon and we have 4 rooms. So we have 4 patients coming, and one room is doing setup. Setup takes a longer time. Even if you do cone beam CT, then somebody has to look at the alignment and make a decision that if the alignment is proper or not. And if you are doing very high dose treatment, the physician has to be available to make sure that he is okay with the alignment or positioning before you treat. So by the time one room is setting up patients, other room is treating, the waiting time is only a couple of minutes. Okay, not that long. But sometimes you have a breath hold patient. Breath hold patients take longer time to be treated because they have to hold the breath and you irradiate, then they relax. You wait for some time. In that process, it may take longer wait time. But that has never been an issue. If there is some patient in urgent need to be treated, they communicate with each other and try to get them high priority. And in your system, there is a priority level you can set up. Okay, all the rooms start with the same priority, but for urgent cases like that, they can change their priority level so that they will get the beam as soon as it becomes available. So these are things that are, yeah, so that's why single room solutions are much better. You don't have to wait for the room beam. This is the Mavian system. In one room they have everything. Okay. And this is the IBM facility. The Proteus 1 is the machine which has a LINAC and it only treats patient one room. Okay. And there's a Proteus Plus, that's what is in Apollo. And I think that's that we have in Tata Memorial also. They have multiple rooms. Okay. There are multiple rooms. And one LINAC is the cyclotron is feeding to all the rooms. Trends of recent proton therapy system, how the things are moving. All scanning ports, no passive scattering. I have already mentioned. Everybody is going for active, passive, discrete scanning. Smaller size, one room, proton beam therapy, small accelerator, robotic couch. You have 6 degrees of freedom. You can set up, align the patient very well, not only by translation but also rotation, and pitch. So you have better onboard volumetric imaging, cone beam CT on rail, surface imaging system, real-time fluoroscope guided proton therapy that I mentioned, range verification devices. One of the things I probably mentioned earlier, we only know where a proton stops in water because we do the measurement, and water the calculations and all kinds are very accurate, and we do our beam commissioning by measuring data in water. But inside the patient's body there are inhomogeneity. What we see in the image is called Hounsfield units or CT numbers. The same CT number can correspond to different electron density, correspond to different material also, because that is some degeneracy. You cannot distinguish the material by that much by Hounsfield units. Same kind of different kinds of fat may have the same HU, but their stopping power may be different. So we don't know where the proton stops in the body. So that's something called a range uncertainty. Okay. So how do you reduce that range uncertainty? Provided you can measure them during the delivery, what is the range where the proton is stopping. And there are some devices that are available, that's called prompt gamma imaging, cameras that's available, very expensive and experimental. And then also PET imaging can do something. Ion acoustic imaging, you can use ultrasound arrays, transducers to also know the range of the proton beam. These are all developmental work. If anybody is an engineer and wants to do something to help with the proton range verification, this field is wide open and a lot of work needs to be done. PET imaging, it doesn't work that very well, but this has a lot of potential also. And then next trend is rotating chair with fixed beam. Okay, that's what it is, that cost of the system will go down, and that is not a concept anymore. There is a center being built, the Leo Cancer Center, and they are marketing this, and a lot of people are waiting for these kind of things to be available. Okay, this will popularize the proton therapy and make it accessible to many patients. Okay, so that many patients can be treated with proton and get some benefit out of it. In summary, okay, this is all you need to know from all these hours we spent together. Proton beam has a back peak, proton stop. Okay, that is the one. What is proton stop? A sharp dose follow-up longitudinal penumbra. Narrow beam from oscillator is spread by 2 methods. Passive scattering proton therapy. A range modeling we use to create the SOBP longitudinally. 2 scatters are used for transverse broad profiles. Field specific apertures compensators are used for dose conformity. Pencil beam scanning. Energy stacking is used to create SOBP longitudinally. Magnetic scanning is used to spread the beam in the transverse direction, like electron beam scanning used in TV. Inverse planning is used to optimize the position of the intensity of proton pencil beams for dose conformity. Minimal use of field specific apertures. What next? That's done. So I told you what the proton therapy system is. Okay. Any questions? I'm not done with my all the things, but this part of the proton delivery system, I told you whatever you need to know. There are many things you can know. You can go and dive deep and get more kinds of things depending upon your interest. Okay, so that's happens. But as a practicing medical physicist, this is probably good enough. Okay. Okay. Let me go back to the next lecture. If you want, you can take 5 minutes break. Okay, if you want. If you don't, that's good. Then we can finish quickly. Okay, good. Yeah.
Sir, in the previous slide you mentioned about snout. What is the purpose of this snout?
Very good question. Snout is where the field-specific, patient-specific, field-specific devices are placed. Like in passive scattering beam, you have apertures, compensators, and they have to be placed in the snout. And they have to be moving, they are movable snouts. So that depending upon the patient position, you wanted to move away so that it is not colliding with the patient's body, okay? In scanning beam, you have an energy absorber. The energy absorber is put there in the snout, okay? That snout is something where patient-specific devices can be placed, okay? So if you have an aperture for some reason, then you can place it there. Okay. So that's called snout. Does anybody get what snout is? And why you need a snout? Where is that snout? Let me see if I can bring that snout. Do you see a snout? This is the snout here, okay? This is where the apertures and compensators are put here. The range modulating wheel is put somewhere in the upstream. You see, this is a range modulating wheel. It rotates with 400 RPM, revolution per minute. And do you see, let's probably just clarify it, where is the range modulating wheel? Here, there are some steps here. The material steps at this location, the steps that take water equivalent thickness of those steps is the highest. And at this it is the lowest, okay? So what happened is when it is rotating, the proton beam is hitting different amount of material along its beam path. So that the pristine Bragg peak is moved closer and closer to the, at the deepest point, it will move to the closest to the surface. At lowest level, it will stay away from the proximal part. So that way you can create a spread out Bragg peak. Where is my spread out Bragg peak? Why is it called Bragg peak? This is the spread out Bragg peak. Bragg is the person that who did a lot of work, and maybe he is the person who came up with the concept of a Bragg peak. So that's why this peak. So that's why it's named after him, Bragg peak. So not to brag about the peak, but it's Bragg is a person, okay? But we always brag about the Proton Bragg peak. So that this is all we have. We can do better job. Let's see what, yeah.
So since you have been working with the proton-based therapy systems, what kind of side effects have you observed in the patients? Are there any side effects?
No, there is no proton specific, because what happened is as I told you that once your beams are modulated, if you are using only small number of fields, the surface dose is higher, the skin dose is higher. So normally patients who are treated with protons, they get little more skin reaction, but that's compensated by other reduction in other toxicity, okay? Skin reaction is a major concern, specifically for head and neck cancer patients, okay? And for prostate patients also, because we only use two lateral fields for prostate patients, and they are treated sometimes up to 7600 centigrade. And so that's why they get about 3000 to 4000 of a dose in the skin. So that is some concern are there. And also some patients skins are very radiation sensitive, so they get also some kind of skin reaction, okay? So that is one of the things. Besides that, there may be some higher incidence of cardiac toxicities for lung cancer patients, because protons, the heart provides, lungs is a very low density object, protons just pass through. So and sometimes that the beam direction is such that the heart is in the path of the beam, so naturally heart stops the protons and takes the beating, okay? So you have to be very careful about the irradiating some areas of the heart that with a reduced dose. So nowadays, the physicians are not just drawing the heart. They are going and doing soft volumes of the heart and telling them that don't treat this much of the tolerance of these structures are this much, how much volume can take, how much dose. They give us, the physicians give us a DVH matrix. So we have to match them with the planning. And as I mentioned, by using multiple beams, you can sometimes get a better plan. And specifically if you have a quasi arc, like you use single energy layers from multiple angles, then you can also achieve better NTCP. That is the direction the field is moving. And we have to also think of other biological aspects, that how you can give the dose that the target needs and reduce the dose to normal tissue complexity. Otherwise, okay. Another major problem with proton therapy is the brain treatment. The base of skull treatments, as always, for some reason, the tumor grows close to brainstem. Okay, the tumor grows close to the brainstem, and brainstem is hugging to the target. How are you going to spare it? So this is a nightmare. This is a nightmare situation. So sometimes the targets are sacrificed. The dose coverage to the target is sacrificed, and then see, as I told you, the major way of reducing dose to the normal tissue in a proton beam is the longitudinal penumbra. But in your longitudinal penumbra or the range of the proton beam is not very well known. So you have to add some uncertainties in designing your beam, so the target is always covered. So you always over range the beam to the target. Target is located at, suppose say 10 cm, you add about 3.5% of extra margin longitudinally the beam to stop. But if your brainstem is sitting nearby, you don't have the luxury of adding that much of margin to it. So eventually some protons will stop in brainstem if you want to cover the target. And once they stop in the brainstem, the LET is high. Once the LET is high, the radiobiological effectiveness is high. So brainstem necrosis is something that happens with the proton beam. But there are many benefits also, because some of the organs can be spared very well. So in your planning, we try to reduce the brainstem dose as much as possible, not shooting the beam towards brainstem, but trying to spare it by lateral penumbra as much as possible. So we have a sharp knife, but that sharp knife has to be wisely used. If you don't use wisely, you may cut your finger. That's what happens, okay? So that is how the proton, that's when we plan and all kinds of things, that is our major responsibility. Just to make sure the dose you are giving to the target are still robust enough under those uncertainties, and the OARs are also safe under those uncertainties, okay? So that is called, nowadays, something they term called robust optimization. So we do robust optimization, we do robust analysis. You take the uncertainty, you look at the uncertainty scenarios. Of course, nobody knows what are the uncertainties. That's a major thing. But you do some hand-waving intuitive argument, and based on that, you create a number of uncertainty scenarios. And with that uncertain scenario, you optimize the dose distribution to be good, robust enough to cover the target, and also safe enough to treat the target. Okay. So this dose planning and evaluation takes longer time compared to photon plans. And another thing is, that is a topic I have to cover, that's called uncertainties in proton beam therapy. That I'll do it on Sunday, okay? Good question. Anything else?
What is the typical planning time?
It's long. And specifically after the spot scanning beam, because the intensity modulated beam, you see, you have to wisely tell what you want. And you have to do your objective definition, the optimization objective defined very well to achieve that goal, okay? So that's why it takes longer time to achieve, and also this treatment plan dose calculation is pretty slow. You see, Monte Carlo based now, before it used to be pencil beam based, but pencil beam based dose calculation have a high inaccuracy. So now it is Monte Carlo based, but it takes long time. And also if you have a large target, and it takes longer time because your calculation volume is long, And if you are doing robust optimization, it takes even longer. Okay, so and also it goes through different iterations. The dosimetrist does a plan, then physicist looks at it. Most of the times physicists try to come up with some better plans, because whatever dosimetrist is created may not be optimal. So naturally physicist has to try something different, and then it goes back to dosimetrist, then it is sent to physician. The physician may have certain objections to that, how the dosage looks like. So it goes to about 2 to 3 iterations. Okay, so that's why it takes time, and also you have to do a QA. You have to do the QA before the patient is treated, because you want to make sure that everything is being transferred to the electronic medical record or a treatment control system, and they are functioning and all kinds of things. So usually we give a 7 days. Yeah. By the time patient comes for a simulation, you see the contouring takes a long time. Although artificial intelligence and machine learning has reduced the contouring time, but then they are not completely satisfactory or not accurate, because sometimes you see, I see sometimes the spinal cord is sitting somewhere in the heart. Okay, so then what do you do? Because for some reason that the deformable registration is doing something crazy. Okay, so that's why the artificial intelligence is good, but has to be is not robust enough, so that your manual examination or contouring is completely eliminated. Not now. It is reduced. Some cases works very well. You train a good model, it will work. Okay. In order to train a good model with machine learning, you need a large number of data, all kinds of things. So, but the field has come a long way. Before the drawing contours by hand one by one, now you can run the script and it will give you some set of contours to refine. Okay, so that takes time, and then the dose calculation and beam selection, all kinds of things. So 7 days. We can create a plan in 1 or 2 days, okay? But the people are busy with many patients. It depends on the patient load also, because they cannot work on the treatment planning system doesn't allow 2 people to open the same patient simultaneously. And then if you have too many patients doing, then it crashes. All those practical limits, all the practical limitations, that has been factored into to decide when we want to treat. Of course, we want to treat as soon as possible. If you have an adaptive plan, you can't wait 7 days. It has to be done right away, because there is some change has happened and you have to adapt it. So that they take precedence. They have to do fast. New patient can wait for a couple of days, but the patients who are under treatment and they need a plan to be adapted, they have to be done right away. Okay.
So about that adaptive planning, like what types of changes are most commonly seen in the patients? Except you said that moving targets. Like what are the changes that?
Basically, that when you immobilize the patient are not anxious at that time. So the devices you make at that time, and by the time they come for treatment, there is a lot of difference in the positioning. So like say neck position for head and neck cancer, they are very tense when they come for simulation. And they put their neck or something, body is squeezed, is the stress and all kinds of things. And then when they come for treatment, they are already little bit comfortable. And also these masks, the masks that are created, they sink sometime after some time. Okay, they sink, so they don't fit anymore. Okay, so all those kinds of things that creates a problem specifically for spot scanning. For passive scattering beam, you have broad beam, 3D planning, no inverse. Here, your sharp spots are being created to create, because physician wants a very sharp dose follow-up. And you know that in IMRT, when you have a sharp dose gradient, your plan is most unrobust. That's possible to failure in small changes. You see, patient sneezes, it can move up to 2, 3, 4, 5 millimeters. Okay, so how do you account for those kind of things, that when patient comes after treatment, then you see that is one of the things. And sometimes in long cases, people have some pleural effusion. That's a disaster, because that's liquid builds up, and then you suddenly, if you are not doing 3D imaging, or it is not visible in radiographs, then you may be treating something completely different. That happens. Okay, Patient comes with pneumonitis, patient comes with some kinds of or fluid buildup. And that's why in proton planning, in X-rays, they are a little bit more forgiving, okay, because the dose change in the longitudinal direction is about 4 to 5% per cm or even less, 2 to 3%. But in protons, if you are in the Bragg peak region, the sharp dose follow-up is 30 to 40%. You may not treat the tumor at all, or you may irradiate the whole critical organ if the beam is passing through different path length, okay. So that's why the anatomical change is very important. So before we didn't have the 3D cone beam CT, so that's why we used to do very frequent CT scans. But now we have cone beam CT, then you can look at it what change has taken place, okay. You can nowadays a trend, there are many places who are doing it. We have not gone that far because of some reason. You can take the cone beam CT and do an approximate dose calculation. It's just approximate. Then you look at the delta. What happens is that the same dose calculation is done in every fraction of the treatment and see how it is changing. If you see a large change, then you go back and acquire a CT scan and do a planning. Okay. Most important thing is the setup. The patient has to be comfortably positioned so that by the time they are simulated and coming for treatment, the changes are minimal. Okay. So what we do now, patient comes, just take him to the couch, show him the devices, all kinds of things. Don't build the device yet. Let the patient get up, take some break, and then again come back so that he is a little bit more relaxed. So that way the anxiety is not there. And then you create the molds and all kinds of things. That may work, okay? But we are in this view that we go through a lot of aggravation, specifically for head and neck cancer patients. In head and neck cancer patients, the adaptive plans are very frequent. After 2-3 fractions, you see that dose distribution is looking terrible. Because the planning was done in a less robust way, because there are some regions of high dose gradient, and if you have not desensitized them, then naturally they will be affected, okay? So, and then the patient positioning, all kinds of things. So we are trying to do the devices one day and don't use it, don't simulate the patient on that day. Simulate the patient next day. By that time the devices will be stabilized, so patient will be little more relaxed. So then you do the imaging and do the planning CT. But this has not been bought by the physician, so this is physicist wish list. But then you have to have another room where the devices are made. The patient has to also travel. Sometimes proton patients come from far away and they want to finish the treatment and go home as soon as possible. So these are some practicals. Did I answer your question? Okay. Let's see what else we want to do today. Yeah, please keep on asking questions. Yeah.
Intensity modulated RT.
Hmm.
You said that dose distribution is optimized in a non-homogeneous way. But how is it different from the VMAT?
See, VMAT is done with X-rays. As I told you, the X-rays, the small change in a HU, Hounsfield unit, of or electron density, doesn't make a very severe change in the dose distribution. If you the effect of a small change in the HU or electron density, the dose distribution is not affected that much. But a small change in the proton stopping power, okay, makes a large difference in the dose distribution, okay, because of the uncertainties in the range. So that's why we try to avoid the beam passing through some of the structures which might be changing or where the HUs are not very well known, okay. So like a dental implants, okay, dental implants create not only their stopping power is not known, but they create a lot of artifacts. Those artifacts, if you do a plan with X-ray beam and with some approximation, and then you change the artifact HU, and you see the dose plan distribution is very robust. But for protons, if you have not properly determined the HU of those artifacts, that what are they really, then if you slightly change it, then it will create a big change in the dose distribution. So that's why having artifact-free CT images is very important for protons, okay. There are many ways you can have artifact-free images, like if you can have a dual energy CT, if you have a dual energy CT, that helps you. Or if you can do a MV CT, sometimes those artifacts are gone. Or you can fuse your CT with a MR where the artifacts are not there, and approximately determine that what you are missing in that artifact region and correctly assign those stopping power. Okay, so a lot of work are needed in order to desensitize the effect of a change in the HU and the proton dose distribution. Okay, so that's why proton beam dose distribution is very susceptible to small changes, whereas in VMAT or IMXT, X-ray therapy, the dose distribution is not that sensitive. It is sensitive to setup uncertainties, but these density changes things are a little more forgiving in IMXT and VMAT. Does that answer your question? Okay. Anybody, anything else on what we discussed? Okay.
Sir, one more question.
Yeah.
So as a medical physicist, what role do we play in the accelerator system, as you said, that monitoring or verifying beam energy? So like what other responsibilities do you typically handle?
If you are an intelligent person, it's a great question. I always struggle with this. If none of my seniors are available, I am a senior most person, but some of my more senior colleagues are not available. I do more measurements than anybody else because I don't have the detailed knowledge of what happened, and I am not always skeptical. Maybe something happened in the beam, the patient will be wrongly treated. Let's do a QA. Let's measure some of the things that I know that's good, like the spot positioning. If any time that they come and tell me there is some magnetic power supply failure, I do the measurement of the spot positioning accuracy. Okay, so similarly, if there is something change happened in the ion chambers, power supply, ion cable, then we have to make sure that the ion chamber is, because ion chamber is in the path of the beam, is properly amplified or not. Believe or not, suddenly our beam is very stable. We do not recalibrate the beam even once in a year or 2 years or something. Suddenly, in the morning QA, it was found that the output is off by 3%. 3% is too much for us, okay? Because we have never seen more than 1% change. So what might have happened? We started treating the patients anyway because within 5%. So then we have a meeting with our Hitachi engineers. What kind of change did you do last night? Oh, no, nothing. Our amplifier cable was a little loose. We changed our amplifier cable. Okay, so a simple thing, they changed their amplifier cable. So naturally, what happened is that the charge collection efficiency of the ion chamber has changed. So you have to make sure that, so that's why that day we tell them that any change you think is not affecting, you have to tell us. We will decide that whether this is something that we measure or not. Okay, so we instruct our service engineers not to do too many things without telling us. So we meet with them twice a week because they do their maintenance in Saturday and Sunday. So we meet once on Friday just to make sure they tell us what they are doing, and then we see how the beam health is being affected. Then we plan our QA accordingly. Suppose they do some LINAC maintenance. LINAC maintenance which is creating 7 MeV beam to inject to the synchrotron. That doesn't affect anything. So we know that our synchrotron, so long as synchrotron energy specifications are met, no beam will be extracted. So we don't care about it. But if they do something with irradiation controller, that irradiation controller affects everything. The dose monitor, spot scanning monitor, magnets. So in this case, we do very extensive QA, okay? Just to make sure that everything is working okay. In the middle of the treatment, something happened and they'll come and tell us that, okay, we have to reboot the irradiation controller. And, sometimes they don't tell us. Physicists, because therapists are all running after them. When are you giving us the beam? When are you giving the beam? And under the time pressure, they said, okay, the beam is ready to take it. Okay, so that's when we go and stop the treatment. You cannot treat the treatment anymore. They become unhappy with it. The physicist, everybody is unhappy with the physicist. The therapists are unhappy with the physicist. The physicians are unhappy with the physicist because they take too long and all kinds of things. But that's what our job is, to make everybody unhappy, but make the patient safe. Okay. All right. Anything? Question and answers are always good because you get something I have to tell you without looking at the slides. Okay. All right. So.
Sir, how this synchrotron is producing this beam with multiple
Energies. Yeah.
but this isocyclotron and normal cyclotron are not producing.
No, there is single energy. But then that's why you have an energy degrader. Okay.
For this synchrotron, they are getting into the same thing, same energy. They are exciting by the same force only, and they are still getting these different energies.
Yeah, this is the magnetic field. The magnetic field that determines that the magnetic field is adjusted to keep the beam into the orbit. The orbit depends on the energy of the proton. So by the magnetic field, what you are using to keep the beam in the orbit will determine the energy. So from the magnetic field strength, you know what energy you are getting.
By LINAC, we are just maintaining this energy what we are producing inside this synchrotron thing. When we are producing this proton into this synchrotron, so we are just fixing this energy what we are producing inside it. Then after we are getting it.
Yeah. Then the beam kicking system is tuned to the particular energy. That magnet, the kicking magnet has a particular magnetic field in which it will be kicked, and that's energy dependent. So if the energy has not been attained in the synchrotron, you cannot kick it out. Okay. Yeah.
We are using cyclotrons to explain protons. We are using cyclotrons or synchrotron.
Yeah. Accelerate the protons.
Are there any linear accelerators can also be used?
Yeah. I told you in a Fermilab, in Brookhaven National Laboratory, they have many large facilities, miles and miles long linear accelerators. They can accelerate particles.
I'm just asking about when it comes to proton therapy.
Yeah, no, nobody uses linear accelerator.
No linear accelerator.
No, we have a linear accelerator only to accelerate up to 7 MeV, to inject it into the synchrotron.
Are there any research going on?
Now, there are some kind of a laser guided system and all kinds of things. Some people are doing that kind of dielectric accelerator, something I don't know about them. Okay, there are some literature, but there are people are doing. But basically, you want to have a smaller footprint in a hospital setting. So the making compact system is the goal. So that's why the Hitachi in that synchrotron, they are combining the cyclotron technology, that is called a variable modulated energy cyclotron or synchrotron, something like that, VMEC. So in that machine is vertically very high, but the space wise it doesn't take long space, but it will a high dose rate. It has a combination, it is a hybrid of synchrotron and cyclotron. That's possible. Okay. So the key is to smaller footprint. You don't use a lot of space in a hospital setting. Okay. So that from that point of view, Mabian system is very attractive. You don't need a special space for your cyclotron. Okay. But these are some stability issues also. Once you make it too compact, there are system other things that you have to deal with. Okay.
Just a quick follow-up.
Yeah.
Using the cyclotron, are there any research work that is going on at your place? Basically, like radioisotope production or something?
Now, there are some cyclotrons for that purpose. We have a radioisotope production facility. I don't know much about it. I don't work there. But there's a lot of things that the nuclear medicine people, they are always looking for good agents, imaging agents. So they play with a lot of things, tracers, developing tracers and all kinds of things. So this is not something that I have never worked on this. I only jump for joy when they give us a tracer that which can do the hypoxia imaging, which can do some kind of a biomarker imaging and all kinds of things. In the next development in the radiation oncology will come from the molecular imaging, because the radiation therapy is a modality that we can treat what we can see on images. Okay, now we are not able to see that targets the soft volumes of the target in a molecular level. We are just seeing in a gross kind of a centimeter level. If you look at that, the stem cells which are responsible for the growth of the target, growth of the cancer, those cells, they, you have to look at it, what is the dimension, it's in a micrometer or something like that. So we have to image them where they are. Then only we can design some micro beams to irradiate them. So you see, we have a capability of delivering micro beams, because you can create a micro what is that called, collimator, that which has only openings of micrometers. And then you can use any synchrotron source, not only protons, you can use a X-ray source, X-rays and all kinds of things, irradiate a very small volume. And in that case, normal tissue damage will be very minimal, because the radiation, you see, when there is a war between two armies, okay, everybody tries to protect themselves. So also the cancer cells. The cancer cells are growing because of the stemness of the stem cells. The stem cells hide somewhere, and they have the ability to create a more and a different kind of cancer cells. So they are the major generals hiding somewhere. So in order to stop the cancer growth or defeat the army, you have to find that a major general, that who is controlling the army, and by a laser guided bombing, so that you precisely go there and deliver it. That is the ultimate aim of radiation therapy. So the molecular imaging is the key. You can see that where is the most active part of the cancer that needs to be sterilized. Okay? So as you are all young and bright future, think about it. Come up with some bright ideas that you can achieve this goal. Okay? Work with cancer biologists, work with diagnostic or nuclear medicine physician and physicist, and come up with an imaging method where you can really see them, see the malignants in a cellular level or molecular level, and then irradiate them. Okay, that will be what? Molecular radiation oncology. Okay, there's a name for that. That's called molecular radiation oncology. So I am giving you too much of work to too much of thinking for the future. Okay, but the current status is not that way. Current practice is pretty broad, pretty gross. Okay, so let's see what I want to talk to you about next.
The thing that you mentioned about the radioisotopes, in a hospital, if there is a proton therapy system already, can that system of cyclotron be used to generate radioisotopes for the nuclear?
You don't need that much of energy. This is cyclotron is too big, but you can use it in principle. But it is just that having a very expensive machine to do your work, because you can get a small linear cyclotron to do your work. So why do you want to spend? If it is there, you may be able to do some activation, but that has to be the whole procedure. That using high energy to irradiate and all kinds of things has to work out. These machines are not made for that purpose. That low energy cyclotrons that are needed for producing radioisotopes are much less expensive and doesn't need that much of a space. So, and also these machines are busy treating patients. So why they don't have time to give you this. But this is an interesting idea, but I am not knowledgeable enough to tell you whether it is possible or not, honestly speaking, because I have not worked in that field at all and not interacted with the people that who produce this radioisotope. But it's an interesting thing to make the best use of your resources. If it works and you don't have a radioactive facility to produce radioisotopes, then you can use them. Okay, it is a good thing to explore. Look at the literature. Even I don't know doesn't mean that the knowledge is not available. The knowledge is available. You have to just look for it. Okay, if there may be some people might be using it, but I don't know anybody is using that one. Okay, the initial proton therapy started at Harvard Cyclotron Laboratory. That Harvard Cyclotron Laboratory was used for physics experiments. Okay, they were not producing this imaging or the nuclear medicine and the radioactive sources, but they are using for something else. And then they thought about it, and then they used it for treatment. And then the whole proton therapy and the community proton therapy modality developed as a treatment, as a good treatment modality. Similar thing, you can always degrade the energy, the cyclotron energy, by putting lot of degrader material upstream. You don't need to change the energy selection system. You can always put a very big, thick plastic phantom in front of the beam, so the beam will be reduced to very low energy or whatever energy you need to irradiate to the target to get a radioactive source. It's possible, okay? But this is only producing protons. But that other, in the cyclotron can also do other isotopes also, okay? So this depends on what you are irradiating and what you are expecting to get out of it, depending upon that. If you need proton beam, it's okay. Like a proton boron capture, boron neutron capture therapy or something like that, okay? Recultures, yeah. So that happens, you take the proton beam, irradiate it to some beryllium target or something like that, boron target, and then you produce neutrons. And you use those neutrons can be captured and they can create a lot of benefit into the patient, okay? Boron neutron capture therapy, is that called?
Proton neutron capture and PBC proton boron capture.
Yeah. That's what happened. Yeah. So there are a lot of research going on in this kind of thing. We used our proton beam to do that experiment also.
We can use lasers also for this because lasers we can accelerate the proton.
Yeah. Laser accelerated beam is possible, but for some reason that the power of laser that you need is very high, and that's not available. That nobody has a. I have never seen a laser guided proton therapy system, laser powered proton therapy system yet in the market.
We also get almost 100 MeV of protons. We also get 100 MeV almost.
Yeah. You can get up to 100 MeV. You can treat some patients. Actually, you can treat ocular melanoma, all kinds of things that you can use that one, and that's possible. Okay, no problem. That's possible. Yeah. So next thing I have in my lecture is the dosimetry of a proton beams. Do you want to start? How much time we have? This is now 3:30 now probably. Time is 3:30. Okay, so we have some discussion now, that's good. So what my plan is, on Sunday, I'll give you some data and I'll give you a worksheet to all of you to do a beam calibration. So you become an expert on calibrating the proton beams, okay? So that's what my objective is, to do and we will also do tomorrow. I have invited a ray station proton expert to show us the treatment planning system, how the proton treatment planning is done. So he will give a 1 hour lecture or show us how the proton treatment planning system works. Then I will show you some planning examples tomorrow on the tutorial. On Friday, we will do a beam calibration and also look at some other commissioning aspects of a proton beam, because one of the major job or primary job for a physicist is to commission the proton beam in the treatment planning system, develop a QA procedure. When once the system is bought, once the engineers have installed the proton beam is available, it is your job, a physicist's job, to take all the measurements for the commissioning of the beam in the treatment planning system, and to model the beam in the treatment planning system, to calibrate the beam, and to develop a QA procedure, and to develop a procedure for a treatment plan, patient-specific treatment field verification. So those are things we will discuss on Sunday, okay? Maybe tomorrow some, and tomorrow will be mostly for knowing about the treatment planning process, okay? Something like that. That's a very important thing. Okay, let's look at in half an hour the dosimetry of a proton beams. Dosimetry of a proton beams means that how to measure the dose from a proton beam, how to measure or determine a dose from a proton beam. Where I am? I am supposed to finish the seven lectures today, but I am at 6B, so I have to continue some tomorrow, okay? No problem. So long as you are learning something. Let me stand up. Enough sitting. Dosimetry of proton beams. Detectors used to determine the outdoor dose, dosimetry under reference condition. Okay, I'll explain them when time comes, okay? Let's quickly go through. It's not that I'll finish it in half an hour. The same detectors used for photon and electron beam are used for protons. There's nothing different. You don't have a proton specific detector, okay? The same detectors, but you have to see what kind of different how they respond to the protons. You need to know how they respond to the proton and correct for it, okay? So calorimeter, ion chamber, Faraday cup. these are used for absolute dose measurement. Because the calorimeter, the calorimeter can also be used for absolute dose measurement of any source. Because calorimeter works in this principle. You irradiate some matter and the temperature rises. You measure the temperature, and from the specific heat you determine how much of a heat is given there, and that's the energy. And you know the mass of the calorimeter material, then you determine the dose you determine the dose absolutely. There is no reference needed so long as you know the material property of the calorimeter. Okay, so calorimeter is one of the absolute dose measurement devices. Ion chamber. You have in the ion chamber you have a volume. You have a volume of air, and you apply a voltage, and when the radiation hits the air volume, it ionizes air. And we know how much energy is needed to generate one ion pair. So if you know how many ion pairs are generated, you multiply by the energy for one ion pair, then you get the energy given to that cavity. If the cavity volume is well known, you know from the density of air and from the volume you can determine the mass. But the problem is most of the times the effective volume of the chamber, air volume, is not known. So that's why most of the ion chambers have to be calibrated into a known dose. The dose is very strong. The dose that you are giving is very well known. So that's why cobalt-60 source is used to calibrate those ion chambers, because the cobalt-60 source is a very stable source. You know today what is the dose, tomorrow you can calculate the decay and then calculate the dose. There is no electrical power supplying and is supplied to generate the radiation source. It is naturally radioactive and it has a long half-life, 5.5 years as far as I remember. Okay, so that's why ion chamber is not a true absolute dose measurement device, because you have to calibrate it, because we don't know the exact volume of the effective volume of the air in the chamber. But once you calibrate, then it is very stable. So that's why ion chambers are also considered absolute dose measurement devices. Faraday cup. In a Faraday cup, what happens is a proton counting device. It counts how many protons are passing through. And if you know the stopping power, and then you know the fluence, and multiply fluence with the stopping power, and that will give you dose. So these are the three devices that is used for determining the observed dose from proton beams in a charged particle. For relative dosimetry, ion chamber can also be used as a relative dosimetry. You don't have to know the absolute dose. You are looking at a relative dose to a reference point. Films are not absolute dosimeters. They have to be calibrated, and that they are good for relative dosimetry. All the solid state detectors like thermal TLDs, diodes, diamond detectors, optically stimulated luminescence detectors, scintillator plates, liquid scintillators, gel dosimeter, all those things can be used for relative dosimetry. The problem is, except ion chamber, all these detectors are LET dependent, because when the proton deposits the dose, you see in the distal part of the dose deposition, the LET changes rapidly. So you cannot, in order to get the response, the response of these detectors are LET dependent. So you cannot take the same, measure the dose without knowing what is the LET response. So most of the times these things are measured, used to measure the dose profile where LET is constant. That the LET is not varying from point to point that you are measuring. So that's why that, and even sometimes some of the detectors like gel detectors, liquid scintillators, or scintillation plates, they have something called a quenching effect. In the high LET radiation region, some of their signal is quenched. So that's why you get a lower response. But that you have to quantify. A lot of people have spent a lot of time to correct for the quenching effect without much success. So that's why you have to be very careful when you are using it. You can use them to do a lateral profile where you are expecting the LET is not changing in this direction. Okay? If the LET is changing, then you have to correct for the LET response. So what you do is you can also do the calibration. If you know the LET of the beam where you are doing the calibration, then you have a LET calibration curve also that you can use. to quantify the LED dependence. Okay, so if you want to know more about this dosimeter, this is a good reference for the review article. You can see it. I consider it a very good reference source for proton beam dosimetry. Okay, dosimetry under reference condition. What do you mean by dosimetry under reference condition? Because the beam has to be calibrated in such a way that whether I calibrate or you calibrate or another person calibrate, we are getting the same value. You don't the condition in which the dose is calibrated or the dose is determined has a reference, some reference parameters, and you always use that. Everybody uses that. So that way the dose calibration does not change from facility to facility. Why it is necessary that all facilities follow the same protocol? Because we do clinical trials. If everybody is doing a different way, we don't know who is giving what dose. So that's the main reason of having a reference condition, is to make sure that all the centers who are participating on these clinical trials, or if you are looking at a clinical outcome from the proton dose or any kind of radiation dose, we should know exactly how much dose you are giving, I am giving, everybody is giving. Okay, so that's why reference calibration under reference condition is very important. Okay. So if you are using a device which needs to be calibrated on a known dose, that calibration should be traceable to a primary standard lab. Some primary standard lab is there, your chamber is calibrated with respect to them, my chamber is calibrated with respect to them. Sometimes it's difficult to go to the primary standard lab, then there are secondary also, that's called standard dose laboratories also, that they can provide that calibration, because they have a chamber which is calibrated with the primary. Okay, that's what you can do. I think in India you have some, maybe BARC, maybe somewhere there you have some secondary dose calibration labs. No primary standard exists for proton beams. The standard for X-ray beams is cobalt 60. Okay, is it true for many brachytherapy sources? Many brachytherapy sources, they don't have a traceable standard. You just use it with reference to a calibrated well chamber and all kinds of things. But there's also many brachytherapy sources don't have a standard calibration also. Okay, so calorimeter will be good primary standard for proton beams. But there are also uncertainties. But there are some dedicated calorimetrists. The one is in Canada, they have a national research laboratory, Ottawa, and one is in England. There are two groups. They have dedicated their whole life in developing proton calibration standards with calorimeter, and they claim now they have a portable calorimeter which can be sent to different proton facility, and you can calibrate your ion chamber with respect to their calorimeter. Okay, so I already stated that calorimeter based standards are being developed. Okay, let's look at what is the calorimeter principle. If a material of known specific heat is irradiated in adiabatic condition, that means none of the heat is lost. All the heat is staying wherever it is irradiated. That is a very difficult condition to meet. So that is one of the difficulties in calorimetry. You have to have a adiabatic condition that nothing is lost. If something is lost, then the heat is produced, but the irradiation is not properly measured. So it has to be maintained. You have to maintain the adiabatic condition. The absorbed energy is converted to heat, and the temperature of the material will increase by delta T. Then dose will become, this is, I have forgotten what is this, a factor joules, some factor here times C into delta T. Oh boy, I am becoming too old now. I used to remember this one, something like that. Okay, so the joules constant or something like that. Okay, I'm sorry, my thermodynamics I have forgotten. After working as a clinical physicist for many years, I started forgetting very basic things, and that's what happened. I'll find out and tell you, or if you find out, tell me tomorrow. So there's a constant. This is a constant factor. Heat to some conversion, energy to heat conversion factor or something like that. Okay. So this takes, and from there you can always calculate the dose now. Okay. All right. So these doses can be measured by something called a thermistor. There is something called what is a bridge? Wheatstone bridge. Do you remember Wheatstone bridge? Okay. The Wheatstone bridge. From there you can measure very small changes. Okay. So bridge output signal, for the you can measure these small changes in the temperature. Okay. because the temperature rise is very small. So you have to have the capability of measuring very small changes, okay? Measuring very small changes. Okay, simple theory, difficult in practice, okay? Simple in theory, but difficult in practice. That's what my conclusion from is. Limitations. Difficult in measuring small temperature change. 2 gray of radiation will make the temperature change is 0.5 millikelvin, okay? So very small change. For less than 0.5% uncertainty, you have to have an ability to measure the temperature change with 0.25 micro K range, okay? Uncertainty in thermistor calibration, correction for deviation from adiabatic condition, existence of a thermal defect, part of energy doesn't always appear as heat. Some of them are lost in other processes. Non-tissue requirement of the core material, proton beam related limitations, high dose gradient and the dynamics of the dose delivery can have certain introduce some other uncertainties. But as I mentioned, there are labs, there are scientists, dedicated scientists, they have tried to correct for all these, remove all these limitations, and they have come up with a feasible and viable standard portable calorimeter that you can bring to your lab and to your facility and calibrate, check your ionization chamber calibration, okay? I'll give you my thoughts about how accurately this dose can be determined, okay? I do calibration as much as accurate as possible, but you see, in radiation therapy there are so many all other uncertainties, especially the biological uncertainties. If you lose sleepless nights for 0.5%, it's not worth it, okay? But there are people, dedicated scientists, they want to bring it down within 0.5%, okay? That's possible. I'll show you what are the uncertainties in dose calibration, okay? So these are the ion chamber beam calibration, most widely in practice. There is a protocol that we will use to do our calibration, that's called IAEA, International Atomic Energy Agency Technical Report Series 392 protocol for the latest protocol. This protocol is very has a wide scope. It all not only gives you how to calibrate the proton beam, it also gives how to calibrate the X-ray beam also, electron beam also. It's a very broad. But we, from our point of our need, we have to look at that part of the protocol where it is applicable for protons. It is very similar to TG51 calibration from AAPM, and ICRU, this is another agency that which makes recommendation how to use the protons. So they have adapted 398 and with some small changes. This TRS 398 has recently gone through some revisions because of those people who want to reduce the uncertainties in the dose calibration. So they have come up with some new factors which changing probably by less than 0.5% or something. But we will all, if everybody adapts, that's good. If some people adapt and others don't, then that's bad. So we have to have a time when everybody should change the new system, okay? And you have to have a way how to quantify the dose of the already treated patients also. So that is the problem if you change the dose calibration protocol, okay? Beam calibration is a protocol, uses the NDW from the accredited dosimetry calibrator. That's how your chamber is calibrated for cobalt 60. And because the chamber is calibrated to cobalt 60, you tell me when to stop. What time is now? I don't have my watch.
3:44.
Okay, we have 15 minutes. Okay, well, hopefully I'll finish the beam calibration and reference standard, so we can do something else, start the non-reference condition. Okay, so the beam, the chamber is ion chamber is calibrated for cobalt 60, but you are not calibrating a cobalt 60 beam. So you are calibrating a proton beam. So you have to have a quality factor for that beam determined. How the response of the chamber is going to change when you put it into a proton beam. So that factor you have to know, KQ, okay, in order to determine the dose for the proton beam. Okay, and this protocol requires the chamber to be at a center of a broad beam, spread out Bragg peak. It is not, you don't put the chamber in the Bragg peak. Because why? Because the Bragg peak has a large dose gradient. And if you put a finite size chamber in the dose gradient, then your dose, the dose what you are measuring is changing. Okay, so if accurate position is very, very important. So that's why the beam calibration that when you do in a reference condition, you do not calibrate them in a high dose gradient region. That is also true in a photon beam. You wanted to make sure the dose distribution within the volume of the chamber is as less gradient as possible. Otherwise, you have to make a gradient correction. Okay, that's a gradient correction. In electron beams, probably they do a gradient correction that is applied. In photon beam also there is a gradient correction that is applied. Okay, so the chambers. But for proton beams, the recommendation is that you do in a SOBP where the dose gradient, the dose distribution is very flat. Okay, you can do it also in the scanning beam. As you see in the depth dose curve in the entrance, there is not much gradient. So you can do an entrance dose calibration also. That's called valley calibration. That's possible also. So the important point is you don't put a chamber to calibrate the beam in a high dose gradient region in protons. So what do you measure? You measure the charge generated in ion chamber. IC stands for ion chamber. Conversion of the charge to dose through ion chamber dose to water calibration coefficient from ADCL. Okay, NDW, ADCL. So you have the KQ factor. Then you know how much charge is generated. Your calibration factor gives you the dose per nanocoulombs or something. Okay, so you know what are the nanocoulombs you generate. You have a calibration factor. You multiply it, so you get the dose. Okay, in centigrade. But you have to apply the correction for the quality factor KQ. Certain amount of charge called by dose monitor adjust to get. Okay, what is MU? What is a monitor unit? Okay, just like in a LINAC you have a monitor unit, there is a monitor unit chamber. Similarly, we also define what a monitor unit for your beam. That definition takes place during the commissioning. You define that what is your MU. MU is a certain amount of charge generated in the dose monitor, and those charges normally get digitized. Then you have some pulse counts, and then you decide, okay, 1 MU is this much of a pulse. So that number of pulses is determined so that you get a 1 centigrade per MU in a decent number of pulses. Okay, decent number of pulses. Okay, so that's why that number of charges that from the monitor from the main monitor that you called 1 monitor unit is determined during the commissioning. And normally the manufacturer has done some experiment and done some Monte Carlo simulation to tell you that how many pulses that you call monitor units. Okay, so that's how it is done. Certain amount of charge collected by the dose monitor adjustable to get desired dose per MU, whatever you want, you can adjust that one. Just like you might not have done much calibration in a Varian machine. Varian machine has a potentiometer. That potentiometer you adjusted when I was doing calibration of those machines, but nowadays they have changed probably to something. I cannot tell you because I have not worked with a Varian machine for a long time. So you can ask your colleagues who are working the calibration how their monitor is defined. Certain when there is a potentiometer adjustment, there are certain resistance or certain amount of things that for which the beam is calibrated. If the dosage is coming out low, you change it and to make it to 1 centigrade per 1 MU if that is the goal. But 1 centigrade per 1 MU is not always the goal. If your calibration is 1.05 centigrade per MU, let that be. And you use that your calculation of a dose for other beams for non-reference conditions. But it's a good thing that to get 1 centigrade per MU is always a desirable goal, so that it makes life simpler. Okay. What next? Ion chamber based. Okay. So what do you have? I might have made a mistake, but try to see. This is the NDW. Then is the reading. Then the electrometer that you are going to use to calibrate the beam has also some calibration factor. They want whether they are measuring the correct charge or not. So how the electrometer is calibrated? They have a known charge and see that if the electrometer is measuring that known charge or not. If not, then you have a calibration factor. Okay. So and then you have, because the chamber is open to the environment. Like the temperature and pressure outside, because the air is not a sealed chamber, it's communicating to the outside. and the volume of the air is depending upon the temperature, environmental temperature and pressure. So you have to reduce your calibration to a standard temperature and pressure condition. So that's why that is called a temperature pressure correction. Then of course what happened is, what polarity you are applying to the electrodes in the chamber. The chamber is calibrated on a certain polarity, so you have to make sure that you are doing your measurement in that polarity. If you are doing in a different polarity, you have to apply a polarity correction. Okay, that's called a polarity correction. So your chamber you have to know at what polarity your chamber is calibrated. Okay, in the ADCL. So, and then of course this is the ion recombination correction, and there is a prescription how to calculate it, and then you give the divide by mu, then you get a dose per mu. NDW is cobalt 60 water calibration factor, KQ is the specific chamber and calibration beam. Annual calibration is usually done by ADCL calibrated chamber in water. Daily and weekly monthly checks are done in cross calibrated with an ADCL calibrated ion chamber. So it depends that calibration, sending a chamber for calibration lab to be calibrated costs about $500 in USA, and once you calibrate, then you have a calibrated chamber. So but sometimes there is a money concern that you cannot have so many chambers calibrated by the ADCL lab. There is a waiting time or money concern. So you can do a cross calibration. You take your calibrated chamber and irradiate it to the same dose and see that how much is the response of your other chamber, and then you have a cross calibration factor that you cannot use it for your annual calibration of the beam or TRS 398 calibration. It is just for a constancy check. In a monthly QA, daily QA, you don't need a calibrated chamber. Then you do cross calibration with your ADCL calibrated chamber. So these are the reference conditions defined in TRS 398. It's a long list of things that you have to satisfy. The material in which the chamber is put is water. The chamber type has to be cylindrical or plain parallel. But if the range is very small, then you have to use a plain parallel chamber. We will come to discuss this residual range in detail. Measurement, middle of the SOBP. The reference point of a chamber for plain parallel chamber is the inner surface of the window at the center. For cylindrical chamber, it's on the central axis, on the center of the cavity volume. Position of a reference point for plain parallel chamber at the measurement depth you put it. SSD, clinical treatment distance. Field size 10 by 10, or that used for normalization of output factor, whichever is larger. For small field application, eye treatment, 10 by 10 or the largest field clinically available. So these are the reference conditions. So when you are doing your beam calibration, you have to specify these parameters. You must use water, you must specify what is your residual range and what is your SOBP width, and what is your G reference, where you put the chamber, and what kind of chamber you used, and what kind of SSD you use. Okay, so these are the things that are to be specified in your calibration the sheet. So KQ is determined from the cobalt 60 to protons. Okay, these are the factors: the WAR for cobalt 60 and WAR for proton, and these are restricted stopping power in air to water ratio, air to air water ratio for cobalt 60, and this is for proton beam, P wall, P cell, P, all kinds of corrections that you need. So these quantities are very well established for cobalt 60. These quantities are not very well established for proton beam. So even this water to air stopping power ratio for proton beam are obtained from Monte Carlo simulation, and this is from theoretical calculation. I have not discussed what Monte Carlo calculation. I am hoping all of you have some idea, but we can spend 5 minutes discussing Monte Carlo simulation sometime later. These things are all assumed to be unit 1 for protons. So what happened is this KQ requires you to know this and this and this, and then you can get the KQ. And IAEA 398 report, the authors of that report has done a tremendous job. So they have given, I hope this KQ values. These are KQ values for large number of chambers. So as a clinical physicist, We don't have to go and do this calculation. You just take it from there. But this is not listing all the chambers. But why do you buy a chamber which is not listed? You go and buy a chamber what is listed here to keep your job simple. Okay, so that's why first before you build a proton therapy center, make sure what chamber you need and buy that one for which KQ is available. Okay, so a proton center you spend millions, a chamber costs couple of thousand, so you can buy a number of chambers just for do your redundancy check. One of the things you have to be careful when you do a chamber for beam calibration, how do you know that your chamber is not damaged? Okay, so that is the most important thing for you, to make sure that you handle the chamber correctly, and you have to have a way to know if your chamber is correctly working or not. So that's why when we do beam calibration, we normally don't do with one chamber. We do with multiple chambers just to make sure that the chamber is working. And there is a principle, guiding principle for handling, for checking this ion chamber. So what you do, you have a long-lived isotope. Put that chamber at a particular fixed position and take a reading. And every time you are going to use, put that chamber there and take the reading, so that you know that my chamber is not damaged. Many people don't do it because they don't have a long-lived source and they don't have time to do this. But that is what is recommended. Okay, if you for a responsible physicist, as a responsible physicist, we need to implement that. It's not done in our center. Also, we don't do it. When I was at a small place where I have certain authority to tell people what to do, not to do, I used to do that. Okay, I have a cesium source, I go and put my chamber there, but I didn't have the luxury to have so many chambers. But here we have plenty of chambers calibrated, so we can do cross calibration. Okay, so either you have many chambers to check with each other, or you do a irradiated to a long-lived radioactive source. Okay, in a controlled position, that your position varying, that will change. So you have to make sure that you have designed a jig where the chamber can be put at the same condition that when you took the reference reading. Okay, make sense? Okay. The another important thing in doing calibration is the beam quality specification. What is the proton beam quality? This is a proton beam quality. This is a pristine unmodulated beam. This is a modulated beam. Modulated beam means that is the beams, different Bragg peaks are combined to give a SOBP. SOBP stands for what? Spread out Bragg peak. At least you remember that one. It's no longer a Greek term for you. Okay. So we know what a SOBP is. Okay. At least that much you can tell. Okay. So what happened is you put a chamber at the center of a SOBP here, and that becomes your and this is a practical range where the depth dose falls to 10% of the peak value. Okay, this is the practical range of the beam. Then you measure the distance of your reference point to that practical range. That's called a residual range. That is called a residual range, and that specifies the beam quality in proton beams. Everybody uses that. You can have another definition, but this is the protocol definition. That's a residual range. What residual range is telling that the energy of the beam at this location is such that it has only the range of this much. It can go penetrate up to this much. Okay, so you can this is giving you what is the range of the beam that is where you are what is the energy of the beam where you are calibrating your dose monitor. Okay, so that is the residual range. Residual range gives you the range of the beam, how far it can go from there. From there, how far it can go. That's the residual range. So once you know this one, then your beam quality is specified, and then if you go here, all these KQ factors are given in terms of this residual range. Okay, so you have this PTW Farmer chamber 30302, then you have Marcus chamber rules NACP, and I think there is I don't have it right now, but in the protocol there is a couple of pages of chambers listed. Okay, so that's why you can determine the KQ. But the good thing, another thing to remember, if the residual, this is mostly it is flat. Mostly it is flat, the KQ. But if you put too close to this residual range, where the residual range will be too close? The residual range will be too close if you put the chamber somewhere else. Okay, So if you put that there very close to the Bragg peak, then your residual range will be, what did I moved too far? Okay. Then your residual range will be too small, then the KQ factor will be changing, okay? But mostly if you are in this region, the KQ is pretty flat, which is a good thing, that you cannot make too much of a mistake, okay? So that's why you choose, that's why they recommend you to put it in the center of SOBP. So that way your the residual range is in a region where the KQ factor is not changing much. Of course, this is only 7% variation, but 7% variation, if you put it here, that variation is pretty large. You don't want to use that region to do the calibration. But there are situations in which you are trying to measure a dose in the distal follow-up region, you cannot use the KQ from here. You have to use the KQ from here, okay? But for calibration, don't put it there. For dose determination, you may have to put it there, okay, on dose. Fluence-based reference dosimetry. That is what Faraday cup. So you have the fluence and you have the stopping power, and the dose is determined here. Needs determination of incident particle fluence and a knowledge of the collision stopping power in water. So this SW is known within 2%. So fluence can be measured by Faraday cup, and then you can get a dose, okay? Some people use Faraday cup to do the dose measurement, some places, okay? Because because they don't have to go have a ionization chamber calibration and all kinds of things. So these are the uncertainties in a reference dosimetry. Water calorimetry, the uncertainty is less than 1%, 0.6%. Graphite calorimetry, 1.4%. Ion chamber, the calibration uncertainty is 2.3%. The people who are designing new protocols, they are trying to make it reduce it much below the 2%, which is a good thing. Faraday cup is same, okay? We use ADCL calibrated ion chamber for our reference dosimetry. At a Paul Scher Institute in Switzerland, they use Faraday cup to determine the number of protons per mu, but ion chamber is used to determine the dose under reference conditions. So they do use both. What next? I finished 6. So lecture 7 will start tomorrow, okay? So we will look at it tomorrow, dosimetry under non-reference conditions. We know now, you know where the proton is accelerated, how the proton is coming out of the nozzle, how the proton beam is spread, and you know how to do the calibration. The next thing is how to treat the patient, how to do the patient treatment, measure the dose for treatment planning commissioning. Once you finish treatment planning commissioning, you are ready for doing plan, okay? And then do the patient verification, okay? That's my goal. You do planning, you go and do a dose verification, get ready for treating a patient. So you can go and tell your boss, I am ready to do work at Proton Center, okay? In 5 days. Okay. We'll call it